Now it's time to start looking in more detail at this notion of undoing a derivative. And we are going to talk now about something called the indefinite integral, which I will need to define, and I will do that right now. Undoing a derivative, an antiderivative, is the same thing as an indefinite integral. So let's write out now a definition of an antiderivative and then examine this relationship in great detail. So definition: a function which we will temporarily call large f of x. And this is not a particularly good notation. It's not very informative, but we'll use this large f of x for right now. This function is called and that's an important word here, an antiderivative. I'll get back to why an is important. An antiderivative of a function, little f of x, our usual notation, on some interval I, if the following is true. If when you take the derivative of this f, you get our function f of x for all x in that interval in question. So this is what makes big F an antiderivative. It is something whose derivative equals f. So that is the definition here. And we will find out in a moment that an antiderivative means that there's more than one antiderivative. This is just one of many. Now this is different from when we took derivatives. When we found the derivative of a function, there was only one derivative. Here, when we find the antiderivative, we'll find out there are more than one. In fact, there are an infinite number of derivatives. So here's a visualization of what we just discussed. Here's your function f of x, and by the process of differentiation, taking a derivative, we get little f of x. So little f of x is the derivative of big F of x. Then the going back process would be the undoing process, which we want to discuss. And that takes little f to big F, which instead of being the derivative in this direction is the antiderivative going in this direction. So let me give you an example of how this might work in practice. Suppose big F of x is the function 1/3 x cubed. Now that function is an antiderivative of the function little f of x equals x squared because, well, it's on all the real numbers, as a matter of fact, because when you take the derivative of big F of x, this function up here, which is d dx of 1/3 x cubed, you get 1/3, of course, stays, and then it's 3x squared, and that simplifies down to x squared, which, of course, is little f of x. Now, I started out by giving you this function and showing you that it was an antiderivative. The question of how we start with a function like little f of x and find the antiderivative is another story. We'll get to that later. So here's what we have pictorially given these functions. The antiderivative function is 1/3 x cubed. By differentiating, you get x squared. And going back now, that's our question. How do you do this undoing? How do you go backwards? But let's write a few more things down as we collect information here. Note, just to repeat what I said before, unlike derivatives, antiderivartives are not unique. As I said, there are many of them. And I'll show you why. It's a very easy idea. Here's an example, and this is the continued example from the one we did on the other page. If you take the derivative of 1/3 x cubed, as we know, you get x squared, and that is little f of x. But it is also true for any constant, and we're going to use big C for constants here. If you take the derivative of 1/3 x cubed plus any constant whatsoever, what do you get as a derivative? Well, the first part gives you x squared, and the derivative of a constant, of course, is 0, so we get x squared, which is little f of x again. And this is because the derivative of a constant is always 0. which means any function of this form will give us x squared. And since there are an infinite number of possible constants here, there are an infinite number of possible anti-derivatives. And that's what makes this different from doing derivatives. So let's put this all down in the form of a theorem so we can remember it. If big f of x, and again I will note that this is not the best notation, it's not very informative, we'll get a better one very soon. If f of x is any antiderivative whatsoever, any antiderivative of the function little f of x on some interval I, then so is big F of x plus c, where c is any constant. And the second part of this theorem says, this is part of it, that if you start and you have an antiderivative, you add a constant to it, you still have an antiderivative. In fact, you can say even more. Every antiderivative of f of x on I has the form big F of x plus c for some c. So what that's saying is, if by some means you can discover an antiderivative for a function, however you find it and you verify that it's an antiderivative, verify it by taking its derivative and getting little f of x. By adding constants to it, then you will get all the members of the entire antiderivative family for little f of x. That's it. Any antiderivative will allow you to do that. So, once again, differentiation produces, and I'll draw an arrow here, produces one derivative. And that is a unique derivative. On the other hand, what we're doing now, anti-differentiation, the backwards direction, produces not just one, but an infinite number. And what we do is we call that an infinite family. So it's an infinite family of anti-derivatives. So that, again, is the fundamental difference here. Differentiation produces a unique result, one derivative. Anti-differentiation produces an infinite family of antiderivatives that will differ only by this constant up here. So, to put this in symbolic form, here is f of x, an antiderivative, and by differentiation, it gives you little f of x, which is f prime of x, the picture I've drawn before. This is the one derivative that I mentioned. Now, I want to tell you the picture that takes you backwards. And let's just note here that big F of x can be thought of as big F of x plus 0. That'll help put that into context here. Suppose I start over here with little f of x. And I want to go backwards via anti-differentiation, which is a technique we'll have to learn how to do. Well, what do you end up with? You end up with a family of big F of x plus c's where the c is any constant whatsoever. This is an infinite family. So this set is an infinite family of antiderivatives for the function little f of x. So this is what anti-differentiation gives you as opposed to differentiation. This family, rather than write it out as a set like this or continually use this phrase, although we'll use this verbally, we'd like to have a single symbol for this. So the single symbol that we have in the calculus for this is this symbol. This long skinny s, we'll talk about that again later, f of x times dx. A little strange looking at this point, but this symbol will be a name for the entire infinite family. So this will be a name for this family. And I will explain this notation now in more detail. But this will represent this entire set. So this is not just a single mathematical object, it's really a representative of an entire infinite set of antiderivatives for little f of x. Now let's look at the symbol. Here is that symbol, which we will call in a moment the indefinite integral of f of x. And that, of course, is big F of x plus c. And as the c's vary, you get different kinds of indefinite integrals. But they all are antiderivatives for the first function that we looked at, little f of x. Let's label all the parts of this so that we can be speaking the same language. First of all, this symbol here. That symbol is called the integral sign. And what it is, in fact, is an elongated S, the letter S. And later we'll see where that came from and why this is a good idea. But that's what this symbol is here. It's a long, skinny S. Then the function in here is referred to as the integrand. These are all pieces of terminology we will actually use, so we have to learn them. This function in here is called the integrand. What is this little dx doing here? Well, you can think of it as a punctuation mark, if you like. The integral of something or other, which will go in here, punctuated with a period dx. But it does a little bit more than that. It indicates for us the independent variable involved in this problem. And the independent variable here is x. So the x part of the dx is what tells us what the independent variable is. So that's the reasoning for that bit of notation. And we'll see a little bit further on why that's really a pretty good idea. Then finally, the c at the end is called a constant of integration. And we've already seen that this can be any constant whatsoever. So this is an arbitrary constant. It's a letter standing for its own family of constants. Now, big F of x, as we know, is one of many. So this is one, which is any antiderivative of the little function f of x. So that is one of many antiderivatives. And now this symbol here. This is the new symbol here that we've labeled all the parts of. But now we want to talk about it itself. And here is what I promised. This is called the indefinite integral of f of x. It's called the indefinite integral. Why is it called indefinite? Well, because it represents a family, and depending on what c you choose, you get a different value. So it's indefinite until you choose a c. So that's the reason for the word indefinite. And we can say a little bit more about it. It represents the entire family of all antiderivatives for little f of x. Now, we've said this more than once and shown you now the notation we're going to use for this. But you want to continually keep in mind when you see this object, it's not just a single function of x. It actually represents an entire family. And to make this specific and particular, you have to choose the individual c. And we'll see in different circumstances how you choose such a c. So with the new notation now, we can rewrite what we had before. The antiderivative family, the indefinite integral of f of x dx, under differentiation gives you f of x. That's what antiderivatives do as you take their derivatives. And then the backwards direction is called antidifferentiation. And we could also call it now indefinite, and here's a new word, indefinite integration, producing an indefinite integral in the end. So the forward direction is differentiation, or finding the derivative. The backwards direction is anti-differentiation, finding the antiderivative, also called indefinite integration. And this differentiation here can be written this way. If you take the derivative of this family, whichever member of the family you choose, you will always get f of x back. And this is worth noting. We'll talk about this again. But this is what's happening. You take the derivative of the antiderivative and you end up with the function. This is the piece of symbolism you want to learn. And notice what's happening here. The derivative operator and the integral operator are undoing each other. That's going to be something we discuss at length later. Now, just as a bit of notation so you don't find this baffling, sometimes we write the following. We put the dx away from the end, depending on circumstances. If you have the integral of the function, which is just the constant function 1, sometimes we write that as just the integral with a dx. It looks like there's no function there, no integrand, but in fact there is. It's the number 1, but we tend to leave that out. Or, if you have a function in there, like 1 over x squared dx, sometimes people like to put the dx as part of the expression, and they'll write it as the integral of dx over x squared, and so on. So those are just variations on how this notation for the indefinite integral is used. And just be aware of those. There's nothing important about them. It's just that you will see them in practice and you should be aware of what they mean. We need to develop some techniques for actually finding these antiderivatives or indefinite integrals. So we'll start that up right now. Finding antiderivatives. First, you can use derivatives we know, and we have a lot of experience with derivatives at this point. Use derivatives that we already know to build a table. And this will allow us to find antiderivatives based on derivatives that we already know. And here's what I mean. Let's create a table where I write derivative here on the left, which will be a source idea for us, and over here the corresponding antiderivative. And you can create one of these tables yourself. There is in every textbook a table with all sorts of derivatives and antiderivatives related. Many of those you will memorize, but you have the derivatives usually memorized already, and just jumping to the antiderivatives is not too hard. But sometimes you're going to want to create your own. So just keep in mind that this is always available to you. Let us start it out this way. Let's pose a question about an antiderivative and see what derivative would allow us to answer that question. So for example, if I wrote down the indefinite integral of x to the r dx, or r is any constant, so this is a typical power function. Now I ask myself the question, what function has derivative x to the r so that when I take this antiderivative of it, I get a function out here. So what function ought to be over here whose derivative will equal x to the r? In other words, what function should I put into this box that will give me x to the r here? Well, if you fool around a little bit and think about what you know about derivatives of power functions, you'll see that if I have the function x to the r plus 1 over r plus 1, when I take its derivative, the r plus 1 power comes down and will cancel with this r plus 1 on the bottom, and then I reduce this power by 1. In other words, I end up with x to the r. So this function has derivative x to the r, therefore the antiderivative of x to the r is this function. So this is going to be x to the r plus 1 over r plus 1. And remember, this represents an entire family, so you must always put plus c here to indicate that this is an infinite number of results. Now, there's one thing to note here. When you divide by r plus 1, r being the power, you have to avoid, in both of these cases, division by 0. So we have to be sure and say this only happens where r is not minus 1. So this is going to only happen where r is not equal to minus 1. And so here we have a rule we didn't have before. We now know how to find the antiderivative of any power. What you do apparently is you take the power, add 1 to it, and divide by the new power. Very often it's helpful to have these verbalizations of rules for antiderivatives or for derivatives for that matter. So let me write this down. Add 1 to the power, x to the r here, you add 1 to the power, and then what do you do with that? You divide by this new power. That's one way to remember this rule. And this, of course, always happens where r is not equal to minus 1. So there we have it. We asked a question about an antiderivative, and we used our knowledge of derivatives to find out what function ought to be here to give you x to the r. So you can see that these are undoing each other. And then the notion of having a verbalization for some of these rules is very, very useful. Add 1 to the power and divide by the new power is one that you probably want to have. Let's continue this process a little bit. I will not generate the entire set of tables that you'll see in various books. We'll just look at a few special cases here to give you the idea of what you should be looking for. A lot of this is something that you will find very easy to remember over time. So again, derivative column and a corresponding antiderivative column. This time let's ask the question, what is the antiderivative of cosine x dx? In other words, what function should I put here that will have the derivative equal to cosine x? Well, when I phrase it that way, I already know. I know that if I take the derivative of sine x, I will get cosine x. That's a very familiar one. So the antiderivative of cosine x is going to be sine x plus c. So I have a new antiderivative rule based on this old differentiation rule that I knew. Well, I did cosine, let's do sine. Suppose I want to know the antiderivative of sine x. So I want something here whose derivative equals sine. Well, the cosine is close, but not exactly right. The derivative of the cosine, remember, is negative of the sine. So if I maybe put minus cosine here plus c, maybe that would work. Well, I can check. Another advantage of all of this is if you think you have an antiderivative, then you can check. Take its derivative. If you don't get what's underneath the antiderivative symbol in the indefinite integral, then you're wrong. So if minus cosine x is really correct, if I come back over here and take the derivative of minus cosine x, I should get sine x. Let's see what happens. Well, the minus stays out front. That's a constant. And then the derivative of cosine x is minus sine x. So with the minus and the minus, I do indeed end up with sine x. And you can continue this sort of process. Pose yourself a question over here and ask yourself if you've ever seen the functions that occur in the indefinite integral as derivatives somewhere. If you have, then you probably already know what the antiderivative is, or can look it up. Let's put a couple more down here just to look at some other cases. What about this case? And I'll start over here again on the right. What if I want to know the antiderivative of e to the x? Well, we pretty much understand that e to the x has the derivative e to the x, so the antiderivative ought to be the same, just with the addition of a plus c. And in fact, that's true. The derivative of e to the x equals e to the x. So e to the x is its own antiderivative, the only function that has that property. All right, let's go ahead and look at this case. There was one power case we left out before, so let's look at it now. This is the case where we have x to the minus 1 power, 1 over x in other words. That was precisely the power that was left out of our previous power rule. So the question is, can I find an antiderivative for this? Well, I can't do the add 1 to the power and divide by the power because I'm going to get 0 in the denominator here. However, 1 over x I recognize as the derivative of the log of the absolute value of x, and then with the plus c. And indeed, as I recall, the derivative of the natural log of absolute value of x, we worked that out to be 1 over x. So we now have a rule for the r equal minus 1 case, as well as all the other powers of x. So now we can take the indefinite integral of any power of x. This one turns out to be the log, which is interesting. And then again, you can continue this process as many times as you need it. So that's one thing to keep in mind as we are looking for finding derivatives. Okay. As a second point here, let's mark down some properties of indefinite integrals, which we are going to start calling them more and more often. Even though they are antiderivatives, the indefinite integrals really represent something that will be extended later on when we talk about integrals in general. In the properties, we're going to find out something here that's very familiar. Suppose a, or rather c here, is a real number, any real number, just a constant of some kind. Then here are three rules. If you have the antiderivative, or the indefinite integral, of c times f of x dx, so here is your integrand, c times f of x, the c can come out front. and just leave you with the indefinite integral of f of x. Now that should sound familiar because this rule holds for limits. It also holds for derivatives. Constants come out front. Here are two other rules that you may remember. If you take the indefinite integral of f of x plus g of x dx, then that's the same thing as doing them separately. The indefinite integral of f of x plus the indefinite integral of g of x. And likewise, these two go together. If it's f of x minus g of x, the same rule holds. It's the indefinite integral of f of x minus the indefinite integral of g of x. These all were seen before, all applied earlier for limits and derivatives. So we have seen these before. The notion of a constant coming out front, as it does here. The notion of the integral or the derivative or the limit passing through sums and differences and putting them into separate pieces like this. That is all something we've seen before. These are properties of something called linearity, and since we've already seen them before, it's going to be very easy to remember these now for indefinite integrals. Let's continue looking at our new objects here. And let me give you a note, first of all, on the constants of integration. Because now that we have these rules for combinations, you're going to see some issues arise, and it's probably worth discussing them right away. First of all, never forget a constant of integration when you do an indefinite integral. It's not just something to be left off whenever you choose. Because an indefinite integral, remember, is an infinite family. Do not forget constants of integration. Okay. However, sometimes you may get too many of them. Well, here's one thing you can do to avoid some of the issues. Do not introduce them too soon. You want to make sure you don't forget them, but you don't want to introduce them too soon. And I'll show you in an example what I mean by that. And finally, when you get multiple or apparently multiple constants of integration in a problem, you simply combine them all into one letter C. Because they're all arbitrary, and whether you add, subtract, or multiply them, they're still arbitrary. So you can call them all a single object. So we can combine multiple constants into one, C. All right, let me show you what I mean in practice here. Here are a couple of examples that will show the problems that could arise. Suppose I wanted to do the integral of 2x dx. Now, if you use the rule that says 2 comes out front, I now have 2 times the integral of x dx, the indefinite integral. This is a power of x, x to the 1, so I know how to do this indefinite integral. So that's 2 times x, one more power, makes it x squared, divide by the new power, plus c. And then what you might think, based on your algebra experience, you might think you should write x squared plus 2c here. But that would be incorrect. It is not 2c, it is still c. Now that sounds completely bizarre, because in algebra, 2c and c are just not the same thing. However, remember that here c is just a stand-in. It's a placeholder saying, I'm an arbitrary constant. Well, if c is an arbitrary constant, 2c is an arbitrary constant too. It's no more or less arbitrary. So it makes it easier if you just put the c at the end as a single letter. And you don't have to bother with calling this C1 and then this C2 to keep them separate. That's not necessary. Let me show you again. Similar kind of problem, a little different manifestation. Suppose I want the indefinite integral of 1 plus x dx. Well, the rule I just saw says I can break this into 2. So this would be the integral of 1 dx plus the integral of x dx. Well, both of these are powers of x. And just for the record, 1 can be thought of as x to the 0. So the power rule applies here, as it does here, x to the 1. So I will have here, if I keep my constants separate, which I don't want to do, but let's try that, I would have x to the 1 power, divided by 1, of course, plus c1, plus x squared over 2 plus c2. If you choose to start off this way, and you do have two different constants in the same expression, they do have to be labeled differently. However, we are going to say that when you write the answer up, the final answer up, x plus x squared over 2, you just want to write a single constant. You don't write C1 plus C2, you just lump them all together as C. What most people do is they do not even write the C1 and the C2 here. They'll just write a plus C at the end and then keep that down here in the final answer. So that's the way you want to deal with this kind of strange arithmetic of dealing with the C. Since they're all arbitrary, wait till the end, lump them all together, and just make sure they're there. Okay, what do we have at this point? What integration techniques do we have so far? So far. It's good to collect what we have so far because in the rest of this course, and if you take Calculus 2, you'll be studying integration techniques, and you'll have a long, long list of such techniques. So we want to keep track of the ones we know at this point. First of all, we know that you can use, and of course you can create for use, a table. Secondly, what you can also do, and we haven't looked at it too much, but we will now, you can rewrite an integrand. If an integrand is not in a form that immediately jumps out at you as being an entry in the table, sometimes by rewriting an integral or an integrand, you can get it in a form in order to use the table. So let me show you what I mean by that. Integrals in general, when they are placed in front of you, will not be in a form that just goes right from the table. It'll probably be something where you have to do some work. And rewriting is the first step in learning how to do some of that work. Let me do this first example in which I just need to go directly to the table, no rewriting necessary. And then we'll look at some rewriting cases. Suppose I want the indefinite integral of 2x to the fifth plus x cubed minus 4 dx. Now I have a rule that says constants can come out front and that I can break up by sums and differences. So using them all at once, I will have this is equal to 2 times the integral of x to the fifth dx plus the integral of x cubed dx minus 4 times the integral of just dx apparently. But remember, there's really a 1 in there, and we can think of a 1 as x to the 0, so this is really just the power rule being applied. And then I have 2 times x to the fifth. I add 1 to the power to make that x to the sixth, divide by the new power 6, plus, again with x cubed I do the same thing, add 1 to the power, divide by the new power 4, minus 4 times x to the 0, add 1 to the power, making this x to the 1, divide by the new power 1, just gives me x. And finally, rather than have a c in all of these various cases, I have written no c's, and now I just put 1 at the end. And of course, if you wanted to, you could simplify this up a little bit. 2 over 6, of course, could be written as 1 over 3. But I wanted to show you how this works out at the first attempt. Now let's look at a couple of cases where we have rewriting necessary in order to see what's going on. And the only way to get good at rewriting is to do a lot of problems, so that you'll try various things and start looking for patterns that appear in the table. For example, suppose you had this sort of function presented to you, cosine x over sine squared x dx. Well, this expression does not occur in the table. So I need to do some work here. With sines and cosines, you suspect that there probably are simplifications here. Here's one way to look at this. If I rewrite this expression inside, the integrand, as 1 over sine x times cosine x over sine x dx, I still have the same thing I had before, but now I can rewrite each of these as the following trigonometric functions: cosecant x, 1 over sine x, and the other one is cotangent x. And now, putting the dx here, also don't forget to put your dx's. It's very easy to start dropping them out. As I look at this, here's where you want to use your recognition properties based on what you've seen from previous derivatives. You might say, I think this looks like a derivative. And in fact, although it's not quite cosecant of x, because the derivative of cosecant is minus cosecant cotangent, if I put a minus sign here, now it is exactly the correct derivative. So minus cosecant x, and then again I have to put the c, and now I have the antiderivative of this function. I have found the indefinite integral of this function. And it works because this has derivative equal to what I recognized over here. So your skills at recognition have to develop over time. Here's another example that will involve rewriting. There's no trigonometry in this one. This is just powers. T squared minus 2t to the fourth all over t to the fourth dt. Now this may look complicated, but if you think about simplifying this out, dividing the t to the fourth into the two parts here, look what happens. The first part becomes t squared over t to the fourth. That's 1 over t squared. In other words, t to the minus 2. And then you have a minus 2 here. T to the fourth over t to the fourth is 1. So this is our simplified expression. Now I have a power of t, and 2 times 1, or 2 times t to the 0, I have another power of t. So suddenly this becomes very easy. This becomes t to the minus 2 plus 1 over minus 2 plus 1. You always add 1 to the power and divide by the new power. Minus 2 times t for this part plus c. And notice I didn't even go through the stage of breaking this up into two integrals. As we get more and more sophisticated in our work, we'll just do it this way, directly. Now this, of course, can be simplified, but this should show you how easy this is to work out if you think of doing rewriting at the beginning. And you won't think of it unless you've tried it quite a few times. All right, here's another one, and I will call this one clever rewriting. But it happens often enough that it's worth paying attention to. Suppose you have x squared over x squared plus 1 dx. Now, the division we did in the previous one won't work here because I have x squared plus 1 on the bottom. However, if I use a little wishful thinking, I can get this in a form that will be useful. I have x squared plus 1 on the bottom. I wish I had x squared plus 1 on the top. Now I don't, but if I put minus 1 here, this x squared plus 1 minus 1 is the same thing as the x squared here. But with that in place, I now see that this part is going to be 1. I'll still have the second part, but with luck, that'll be a part I can do. Sometimes you just have to do trial and error. Maybe this technique won't work all the time, but at least it's one that's good to see. Now I have 1 here, x squared plus 1 over x squared plus 1, minus, and I have 1 over x squared plus 1 dx. Now here is another place where your recognition should come into play. You should recognize from your experience with derivatives that 1 over x squared plus 1 is a well-known derivative. And rather than break this into two, again, I'll just go straight to the result. The first one is x, because the derivative of x is 1, minus, and 1 over x squared plus 1 is the derivative of tangent inverse of x. And then finally, I add c at the end, and I have my entire family of antiderivatives, which is what this expression at the beginning represents. So I hope you practice a lot of these, because that's the only way to get better at recognizing the sorts of things you'll have to do to change integrands into something that is a little more workable and will be suggestible from the table. We're also interested in, of course, the graphs of the functions we're looking at, the graphs of antiderivatives in this case. Now, antiderivatives, when you find their graphs, they're usually referred to as integral curves. And sometimes you can't find them directly, so you have to approximate them. One easy technique we can look at is the so-called slope field approximation. But we'll get to that second. First of all, let's define what I just mentioned. What is an integral curve? An integral curve of some function f is just the graph of an antiderivative. So each antiderivative will have its own graph, and that will be called an integral curve, and so there are an infinite number of integral curves. So the graph of an antiderivative of f. So that's just another piece of terminology you want to get used to. Instead of saying the antiderivative graphs, we say the integral curves of the function f. Here's an example. If f, or f of x, is equal to x squared, various antiderivatives are the following. Various antiderivatives are 1/3 x cubed. We saw that the derivative of that is x squared, but it is also true that 1/3 x cubed minus 1, or 1/3 x cubed plus 1/2, and an infinite number of other choices. Every one of these is an antiderivative of x squared. Each one of them is a different curve. So each graph is one integral curve. And of course, how are they different? They're all integral curves, of course, of f. How are they different? Well, by adding or subtracting a constant, all you're doing is observe that these are all just vertical shifts of each other. So once you have one of these, by going up or down visually in the plane, you will get copies of this original graph, and each one of them will be an integral curve of a function. So that's a nice way of visualizing an entire family of integral curves. Let's do a problem that might come up in which integral curves have bearing. A point, say, moves along an unknown curve, and this is what we'll be discovering, an unknown curve. Let's say we'll call it y equals f of x. At each xy point of which we do know something. We know that the tangent at each point of this curve, the tangent line has slope which can be calculated as x squared, the first coordinate of the point squared. What we want to do here is find an equation that stands for the specific curve, that represents the specific curve that happens to passing through this specific point, 2, 1. So, what are we given here? We're given that this unknown curve, whatever it is, has the property that at each point of the curve, the tangent line has slope x squared. Well, that tells me that I know the derivative of the function at y equals f of x, which has this curve as its graph. So I know that dy dx, which of course is f prime of x, must be x squared. So that means that y equals f of x, which I would like to know about, is an antiderivative of x squared. And I have a notation for that. That's the indefinite integral symbol. So the indefinite integral of x squared dx is the antiderivative family of x squared. And if I do that, since we've done this already before, we know it's 1/3 x cubed plus c. Now this is a general answer, but we want to pick out that specific curve that passes through this specific point. And when that kind of information is given to you, that allows you to pick out a particular c value. Since f of x equals 1/3 x cubed plus c passes through the point in question, passes through the point 2, 1, then we can say the following. We know that if you take f at this x value 2, you're going to get 1 on the one hand. That's what the point tells us. On the other hand, here's a formula for the function. If I put 2 in, I should get 1/3 times 2 cubed plus c. Well, this is 8/3, and if I put this on the other side, I get c is equal to 1 minus 8/3, which is a minus 5/3. And suddenly I know what c is. For this specific case of this curve passing through this one point, thus I have that f of x equals 1/3 x cubed minus 5/3 here, because we wanted it to pass through this specific point. So whatever the picture is here, the idea is that if you're in the plane and you're looking at an antiderivative of a function, then all the other antiderivatives are simply vertical shifts of that original function. So you have this infinite set of curves. And if you pick out a point, like this one visually, then there's only one curve that will pass through that point, and that's what we've just done here. We picked out a particular point. Now, what about this situation? What if, just as we saw in a moment ago, dy dx equals f prime of x is given. So we know the derivative, as we did find out in that previous problem, the derivative was given to be x squared. What if the derivative is given, but we cannot find y equals f of x? Perhaps we just don't know enough, perhaps it's impossible, perhaps it's just very hard. What if we have that derivative, which is a lot of information really, but we can't find the function? Can we at least approximate it somehow? Well, the answer is yes. And a very nice simple technique will allow us to do that. And this is one you can do very much by hand. But as you'll see, it's one of those techniques that, although the description is easy to talk about and you can do small examples by hand, it's really something that's best done by a piece of software. And we'll look at that in a second. So this is called a slope field, sometimes also called a direction field. If you study physics at some point, you will be talking about vector fields and so on, and all of this word field will begin to be a little bit more sensible to you. Right now, you'll see what we're talking about when I write this out. A slope field, or direction field, for the only piece of information we have, which is dy dx equals some function, and I'm going to write g of xy, because x and y could be involved over here on the right. For that, what is a slope field? It's a plot of tiny line segments. Tiny line segments with slopes g of xy, because dy dx is the formula for slopes of tangent lines, and that's what this g of xy is also, with slopes g of xy located at a given lattice of xy points. And just for the record, this kind of a problem where you know the derivative like this is what's called a problem that has in it a first order differential equation. Now, we don't study many differential equations in this course, but we will look at this one for approximation purposes. Now, what does this mean? A plot of tiny line segments with these slopes located at a given lattice. You may not know what a lattice is. Let's go ahead and write down what this means by doing an example. Suppose we're given the fact that dy dx has this value, x minus y. And for some reason, this one is pretty easy, but let's assume that we cannot find y from this. We don't have any technique for that. Find a slope field for this. And then we'll see how it helps find what solutions might look like for this curve. Okay, how do I go ahead and create a slope field? Well, the first thing is I want to choose a lattice of points, sometimes called a grid of points. Since we're doing an approximation, we cannot draw graphs at every possible point in the plane. There's an infinite number of points. What we do instead is we pick out a sequence of points that are equally spaced in various directions. We evaluate numbers at those points, and then we look back and hope that the approximation is good enough to give us a sense of what the curve will look like. So what I will do here is take a very small set of points, and I'll choose them around 0, 0, and I'm just going to choose this particular lattice of 9 points. That's all. Now, when you use software, of course, you can choose points at regular intervals, but you can do 50 by 50 or larger numbers to see more and more detail. But I'm only going to do 9 here because I'm doing this by hand. What are these points? This point here is the point minus 1, 1. This point here is the point minus 1, 0. This then is minus 1, minus 1. So each of these are a unit apart in the x and y direction. This point here is 0, 1. This, of course, is 0, 0, the origin. This point is 0, minus 1. Then finally, this one is 1, 1. This one is 1, 0. And this is 1, minus 1. So I have 9 points in all. What do I do with these points? Well, I come over here and I create a table. And the table will consist of 2 parts. And this part on the left will be the xy point. So I will take all 9 of these points and list them here. On the right, I want to find the slope. And the slope at that point will be dy dx, which is g of xy. That's a little small to see, but here is dy dx equal x minus y. G of xy is x minus y in this case. So if I list the points here vertically, and I will read them from left to right across the top, the middle, and then the bottom. So I'll have minus 1, 1, then I'll have 0, 1, then I'll have 1, 1. And I'll put a line here to indicate that was the first row. Then I'll put minus 1, 0, and I'll put 0, 0, and I'll put 1, 0 for the next row. And then finally I'll put minus 1, minus 1, 0, minus 1, and 1, minus 1. So there are all 9 points. These have x and y values in them, so I can calculate x minus y, which will then represent dy dx, which is the slope, which will be in this column. So if I do that for each of these, minus 1 minus 1 will give me minus 2, 0 minus 1 is minus 1, 1 minus 1 is 0, and then so on. I get minus 1, 0, 1, and then 0, 1, and 2. So for each point, I have a slope associated with it. Then what I do is I take these slopes and I use them to draw tiny tangent lines at each one of these points. So here is my grid again, and this time I won't label them. I'll just mark them here so it's a little easier to see. And I have these 9 points, and in each one of these points there's a slope associated with it. For example, at this point here, the slope associated is minus 2. So if I draw a tiny tangent line indicating a minus 2 slope, it might look something like that. At 0, 1, the slope is minus 1. That's the 45-degree slope. At 1, 1, the slope is 0, so that's horizontal. And then I go through the rest of these, and I get a minus 1 slope here, a 0 slope here. You can't see that very well. And then a 1 slope here. There's our first positive slope. Then we have a 0 slope here, a 1 slope here, and a 2. That's a steeper slope here. Now you can begin to see what's happening here. I'm getting a series of these little lines, and if you want to think about a slope field as a field of grass, and these are little blades of grass lying there, that's not a bad idea. Then with these 9, I can't see very much what's going on. But if I had hundreds of them, I could. And now with a little bit of technology, I'll show you that. By calculating more of these, I get a much better sense of what a solution to this might look like. On this screen, you can see that for dy dx equal x minus y, this is the kind of slope field that you get if you have about 400 points instead of the 9 points that I had graphed when I did it by hand. And if you look here in the middle, you see the 9 points in the center look just like what I drew. But with a picture this size, you can get a better sense of what's going on. Notice, too, that if I click on this, there is an example of an integral curve that can be approximated from a slope field. That's the purpose of a slope field. If I take any given point and I follow the tangent line to the next point and then follow the new tangent line and so on, I get a curve something like this. And depending on where you start, you get different curves as you see. So I can start at different points and I get different integral curves, all from this slope field. So I get all these nice approximations. Let's look at a couple of other functions here just for fun. If I look at x squared minus y squared, I get a new slope field. And you can see it looks different, that the patterns here are quite different. If I click in various places, I get very different kinds of curves. But all of these would be sort of unexpected if you didn't have the slope field here to give you some instinct as to what those pictures are. So the slope field idea is really a very helpful one. Let's just do one more just for fun here. X over y. And if we pick out curves here, we get these sorts of curves, and it all depends on where the curve is passing through a point. Again, I could not have done this if I did not have a slope field, and that's the purpose of slope fields, to give us approximations to curves we can't otherwise get a handle on. Continue our look at antiderivatives and how they figure into differential equations. We've looked at approximations, but now let's look at some cases that we can actually do. The antiderivative as solution of a differential equation. Let us suppose, and this is a very familiar situation, let us suppose we know the following. We know that the derivative of some unknown curve y is equal to some function f of x. Now I'll just do little f of x for that dy dx here. Let's suppose we have that. And what we want to do here is we want to find the curve y, which is y of x, that satisfies the equation. That satisfies this equation here. So we have something that tells us what the derivative is, and we want to find the function whose derivative this is. So that is our goal. Suppose now we know one more thing. Suppose we also know that y evaluated at some point x naught gives us a value of y naught. That is to say, meaning that the point x naught y naught lies on the y of x graph, whatever y of x graph looks like. So suppose we have this information and this. What is that called, and then how do we solve it? Well, by definition, this is called an initial value problem. A piece of terminology that's worth learning at this point. It's an elementary sort of differential equation problem. If you take differential equations, you'll do a lot more, but this is a very beginning problem that is appropriate here in Calculus 1. An initial value problem has this form. Find, this is a shorter version of what I wrote on the other page, find y equals y of x given that dy dx is equal to some function f of x, and that y at x naught is equal to y naught. And this, of course, is the initial value. And some people just refer to the x naught, or you can refer to the whole point x naught, y naught. So this is an example of initial value problem. How do you solve it? Well, you have to know something about antiderivatives. If that's not possible, then you might have to approximate a solution as we did with the slope fields. Solve the initial value problem that looks like this, as an example. I know that dy dx is equal to cosine of x. And I know that y evaluated at 0 is equal to 1. I don't know anything else about this function y, but I do know it has this point on its curve, and I know its derivative. Can I get y, is the question. Well, the function here, cosine x, is simple enough that we can do that with what we know. Y, if the derivative of y is cosine x, y is the antiderivative. So y is the antiderivative, and I'll write it this way, dy dx evaluated at dx. And later on in the course we'll talk about this notation and how it suggests certain things. But here, of course, dy dx is just cosine x dx. And that's an antiderivative we know how to do. We need to find a function whose derivative is cosine x. That would be sine x. And then remember, we have to add c because it's an indefinite integral. Now, this gives us y as an infinite family of curves. We want to have one specific curve, the curve that has this property. So we'll go ahead and use that information. We know that if you take y and evaluate it at 0, on the one hand, on the left, you get 1. On the other hand, it has to be this function. So it's going to be the sine of 0 plus c. But of course, sine of 0 is just 0, which means c must be equal to 1. Thus, we have the curve we were looking for. Y of x is equal to the sine of x plus c, and c turned out to be 1 here. This is the specific curve that satisfies this initial value problem. It passes through this point and has this derivative. And that's all there is to it as far as initial value problems go. Of course, you have to be able to do this indefinite integral, this antiderivative. If this is not possible, then the rest of this, of course, can't follow. But for now, we'll be giving you problems where you can do the indefinite integral, and we'll be able to answer these sorts of questions. Exercises. Time to do a couple of those on your own. Let me pose this one to you. Evaluate and simplify to some reasonable level the following indefinite integral. The indefinite integral of x to the 1/3 power times 2 minus x quantity squared plus secant x times the quantity secant x plus tangent x, and this is all under the integral sign. So this is your integrand, this entire long function. So give that one a try and see what comes up. All right, let's look at this. Well, the first thing I'm going to do here is, I notice that I have 2 minus x squared, so I'm going to multiply that out so I can clean this up a bit. And I'm going to expand this out because I don't see this in the table anywhere. What I need to have are powers of x, so I need to write this out. Also, on the right-hand side, I'm going to multiply all of this because, again, I don't see this product anywhere in any table. And I don't recognize it as any particular derivative. So with that in mind, I'm going to be doing some rewriting. And the first thing I'm going to write, as I just mentioned, is since 2 minus x squared can be rewritten as 4 minus 4x plus x squared, this entire integral can be rewritten as the integral of, let's see, multiplying this through, that would be x to the 1/3 times this expression. I will have 4x to the 1/3 minus 4x to the 4/3 plus x to the 7/3 plus secant squared x, that's multiplying these two out, plus secant x tangent x. And this is all dx. And then if I continue to multiply things out and break things apart a little bit, if I break this into various pieces, I see that I have 4, the integral of x to the 1/3 dx, minus 4 times the integral of x to the 4/3 dx, plus just the integral of x to the 7/3 dx, plus the integral of secant squared x dx, and finally one more, plus the integral of secant x tangent x dx. Now I'll have to continue on here, but you may have noticed already I have 3 powers of x. Those are easy to do. Secant squared should be ringing a bell as the perfect derivative of tangent of x. Likewise, secant tangent should be ringing a bell as the perfect derivative of the secant function. So with that in mind, I can continue this process, and I get 4 times, using the power rule for indefinite integrals, x to the 1/3 plus 1 over the new power, minus 4 times x to the 4/3 plus 1 over this new power, plus x to the 7/3 plus 1 over that new power, 7/3 plus 1, plus the antiderivative, or indefinite integral, of secant squared is just tangent x, because the derivative of tangent is secant squared, plus, likewise, secant x, because the derivative of secant x is secant tangent. And then add a c because it's indefinite. And if you want to simplify to some reasonable level, all of this is simple. These powers you probably could clean up a bit and end up with something that looks like this. 3x to the 4/3 minus 12/7 x to the 7/3 plus 3/10 x to the 10/3 plus the rest of it, which is tangent x plus secant x plus c. And that's what you should have gotten in more or less this form if you work this problem out on your own. Let's go ahead and look at another one, and this will be an initial value problem. Solve the following initial value problem. You are given the information that dy dt is equal to secant squared t minus sine t, and you're given the information that y at pi over 4 is equal to 1. See if you can solve that one. Here we go, an initial value problem. Well, I need to get at y from its derivative, and so I know that y of t is going to be the antiderivative, or indefinite integral, of the derivative secant squared t minus sine t, and I'm just going to hope that I can actually do this. Luckily, I recognize secant squared as the derivative of tangent, and I recognize minus sine t as the derivative of cosine, which means that this equals tangent t plus cosine t plus c. That's an infinite family of functions. I need to find out that particular function that has this property, that y of pi over 4 equals 1. So let me go ahead and look at that on this page. But I know that if I take y at pi over 4, I am given to have it equal to 1. That's what I have on the left. On the right-hand side, of course, I put phi over 4 in the new family of functions we just found. So that's going to be tangent of pi over 4 plus cosine of pi over 4 plus c. Now, if you don't remember the tangent and the cosine of pi over 4, we'll do a little picture here to try to bring it to your mind. Remember, we can take a 1 by 1 right triangle. That makes this square root of 2. Each one of these other angles, other than the right angle, is pi over 4. So I can see that what I have here is 1 equals tangent of pi over 4 is opposite over adjacent. That's going to be 1. Plus the cosine of pi over 4, which is the adjacent over the hypotenuse, 1 over square root of 2. And then I have the plus c. So from all of this, the 1's cancel. C is going to be equal to minus 1 over square root of 2. So having c and having form for y of t, I can now write y of t